Hello, everyone, and thanks, Mihal, for the introduction. I try to cut things a little bit short in the interest of time and try to be high level. Feel free to ask any questions offline regarding this work. So in this talk, we are going to talk about two different words. On one side, we have algorithm design, where the goal is to design algorithms in this context objects that can solve optimization problems. There are many algorithms out there, greedy algorithms, branch and bound, LP rounding, dynamic programming, so on and so forth. And in most of these problems, if there is an element which is a strategic element coming from users that you are designing these algorithms for, which usually ignore the incentives and only focus on the optimization aspect. However, in economics, we design mechanisms which are essentially algorithms that part of their input is coming from selfish or strategic agents. And here we are pursuing goals that are economically justified, for example, social welfare. So it seems it's a harder problem, and in fact it is, not only because of incentives, but also because in many settings, especially in modern settings of mechanism design, we have extra complexities due to the feasibility constraints or maybe the multi-dimensionality of the types or private information of the users of our mechanism. Probably for this set of audience, I don't need to convince this is actually the case, but let me just name a few of these settings. For example, you can think of modern setups of advertising auctions when you have to design a complicated slate of advertisement rather than just sorting the items. You can think of the reallocation of the broadband spectrum, which is another combinatorial problem. Even the optimization problem seems to be hard. And then you can think of auctions for cloud computing services. And I'm not going to go through these applications, but the bottom line is, with this complexity, can we design incentive compatible mechanisms that try to maximize social welfare, the total allocated value by the users of the mechanism? So as we all know, the celebrated result of Clark-Groves gives a compelling answer to this question only if you can solve the underlying optimization problem optimally. So what does that mean? So if you can assume that the users of the mechanism, they report their types, and then given those reported types, you can find the outcome that maximizes social welfare exactly, then you can accompany this allocation algorithm with a bunch of payments called externality payments, and you can internalize their externality in some sense and get a mechanism that is not only efficient, maximizing social welfare, but also satisfies the strongest notion of incentive compatibility, basically dominant strategy incentive compatibility. So what can we do in settings that the underlying optimization problem is hard? For example, as I said, in the advertising auction or the dynamic reallocation of the broadband spectrum or the cloud computing, we are going to deal with NP hard problems such as ordered knapsack, maximum independence set, or job scheduling. So one question is, for these settings that you cannot hope for existence of optimal algorithms, can you use the existing non-optimal algorithms that probably are good heuristics, greedy algorithms that give you approximations for this problem, so on and so forth, and somehow transform them into mechanisms that obtain comparable social welfare guarantees? And by mechanism, I mean an incentive compatible mechanism. So unfortunately, there are a bunch of strong negative results regarding these kinds of transformations. First of all, if I give you any non-optimal allocation algorithm, you cannot hope for accompanying it with just a bunch of payments and have a incentive compatible mechanism. This is by now a classic result. And on top of that, there is a stronger statement. There are some allocation algorithms that there is no way that in a computationally efficient way, you can transform them into a mechanism that has a comparable social welfare guarantee. And the final outcome is a dominant strategy incentive compatible. This is for the objective, not social welfare. It was a classic result by Nissan and Ronan, and then Ashnaghi et al. And for the objective of social welfare, the work of Charlo et al. Established this strong lower bound. So now the question is, what can we do? So one approach is, what if we think about a Bayesian setting, where the users or the agents, they have common prior distributions over their types, and the types are independent. And the mechanism designer knows this common prior distribution and only wants to design a mechanism in which truth telling is a Bayes-Nash equilibrium of this game of incomplete information. It might be actually a meaningful assumption in some practical domains, especially when the market attendees, they have information about other market attendees, so they can basically calculate the best response given the distribution and knowledge of other participants of the mechanism. It might not be, but I think it's still like theoretically is an interesting setting. So now here's the question. Given an algorithm, is there a generic way of transforming the algorithm into a Bayesian incentive compatible mechanism that is computationally efficient and is using your allocation algorithm in a computationally efficient way? And the output is a mechanism that has a comparable social welfare guarantee. So this has a strong economic message because it says, if you're trying to maximize social welfare in a Bayesian setting, you can just ignore the incentives and focus on the optimization problem. Once you have a compelling answer to the optimization problem, using this generic toolbox, you can transform it into a Bayesian incentive compatible mechanism that is comparable. It also has an interesting computer scientific message in the sense that it says, in terms of computational hardness, Bayesian mechanism design, even though it seems to be harder, it's not actually harder than Bayesian algorithm design. There is a polynomial time reduction from one problem to the other, which makes them equally hard in terms of computational hardness. So let me try to tell you what is the setting that we are interested in this talk, which is the general Bayesian multi-parameter setting of mechanism design. We have n agents. Each agent I has a type Ti, and there is a set of possible outcomes. We assume the types are independent, drawn from known common prior distributions Fi. And then each agent, given a type Ti and given an outcome O, has a value for this pair of type and outcome. For simplicity, I assume these values are between 0 and 1. Now, a mechanism is basically a pair of an allocation rule and a payments rule that runs the following protocol. It asks the agents to report their types. Given the reported types, picks an outcome denoted by A hat of B, and then charges each agent with a payment denoted by Pi of B. So we assume the agents are having linear utilities, meaning that their final utility is the allocated value minus the payment that they have to pay. And now we run a Bayesian incentive compatible, and we try to design a Bayesian incentive compatible mechanism. So in a black box fashion, let me explain what does that mean. So the mechanism again asks the bidders to report their types, find an allocation and a payment. And we would like, in this game of incomplete information, truth telling to be a Bayes-Nash equilibrium. But we give an extra flexibility to the mechanism to be able to use a given allocation algorithm. Remember, the problem is about transforming a given allocation algorithm into a Bayesian incentive compatible mechanism. We assume this allocation algorithm is given as a black box to the mechanism, meaning that the mechanism can send queries to this allocation algorithm. So a query would be just a profile of types, let's say allowable types. And given that profile, the allocation algorithm is outputting an outcome. And in general, you can think of randomized allocations. So this can be just a distribution over possible outcomes. And now you would like to design a mechanism that uses your black box allocation algorithm in an efficient way and obtains a welfare that is comparable to the welfare of the allocation algorithm if everyone was reporting truthfully to this allocation. Okay, so this object is called Bayesian black box reduction. And what do we know about this problem? So optimal algorithms are easy. This is basically the Vickery-Clark-Groves classic mechanism. Now we talked about some established lower bounds for the DSIC black box reduction. About the BIC, I think everything started with this work of Hartman and Lucier, which appears in AER. And then, so this solves the problem for the single parameter setting. When we think about the multi-parameter, there are two works, Bei and Huang and Hartman, Kleinberg, Malikian. So both of these problems, they basically solve the Bayesian black box reduction for the general multi-parameter setting. When you allow epsilon BIC, meaning that you don't say the truth telling is a Bayes-Nash equilibrium of this game, you can just say it is an epsilon Bayes-Nash equilibrium. No one is going to deviate. No one is going to benefit more than epsilon from a deviation from truth telling. And for a special case of the problem, there are known Bayesian black box reduction. So what we show is actually for the general multi-parameter and general type spaces, no matter discrete, no matter continuous, you can actually have exact BIC Bayesian black box reduction. So let me say the statement carefully. So you give me an allocation black box A, and there is a parameter epsilon. So through a polynomial time computation method, I create a different allocation algorithm A hat and a payment rule P, so that these two form a Bayesian incentive compatible mechanism. And also the expected social welfare that I get from this BIC mechanism is at least as much as the expected social welfare of the original allocation algorithm that I started with minus some epsilon, if everyone were reporting truthfully to this allocation algorithm. And at the end of the day, when we say polynomial time, what I mean is the number of calls to the allocation oracle is not more than polynomial in n and 1 over epsilon, and the rest of the computation is only polynomial in n. Okay? So let me explain a little bit about what's the approach to do BIC reduction that should remind you of ironing in Meyerson theory. So this is called, the main idea behind all of these black box reductions, including us, is type resampling. So what does that mean? So we have agents attending the mechanism. Each one is reporting a type. So which I called it type resampling, that gets the type from each agent and produces a new type, which we call it a surrogate, and then plugs all of these surrogates into the given black box allocation algorithm. And now this allocation algorithm is going to output some outcome, and when we compute the payments. So the structure of the black box reduction at the end is going to be designing these type resampling modules in a way that this final mechanism would be a Bayesian incentive compatible mechanism. And let's actually think about this problem a little bit more. So let's think about the type resampling procedure, which I call it the surrogate mechanism, from the perspective of one agent, agent one. Assume that other agents are actually reporting their types truthfully to the allocation algorithm in the center of the previous slide. And now suppose I want to design what would be the resample type of the agent one. So the first thing I do is I take like so many IID samples from the type distribution of agent one, so that I cover the entire possible set of deviations, roughly speaking. Now I want to pick one of these surrogates to be assigned to this agent. So how do I do that? Through a procedure, I'm going to call it a surrogate mechanism. So as a surrogate mechanism, I ask the agent to report her type. Then given the reported type, I pick one of these IID samples as the resample type, and I plug that into the allocation black box while the other agents have plugged their types truthfully to the allocation black box. This gives me an outcome, and then I charge the agent with some payments. So think of this problem as a single agent mechanism design problem that you would like to design the allocation of the agents to a surrogate and the payment rule, so that this final thing is an incentive compatible mechanism. And then at the end, once I design this incentive compatible mechanism for each agent, I plug them back into the picture to have my final black box reduction. So why this is actually enough for our purpose? In fact, you can show, and I'm going to skip the details, that once you have correct surrogate mechanisms, which are incentive compatible, for each single agent problem, they actually give you a good surrogate in terms of value that the agent gets from the mechanism. And also they don't change the distribution of the type, meaning that the resample type and the actual type, they have the same distribution. Then I can decouple the problem into a bunch of single problems. And I'm going to explain that in a slide. For now, let's actually focus on this surrogate mechanism problem. So I have an agent, it has a type, there are different surrogates. So think of an edge in this picture, which is an edge from a type to a surrogate, meaning that if the agent has a type T and I pick a surrogate Sj, what would be the expected value that the agent gets from this allocation? Remember, so we plug the surrogate into the allocation algorithm, and the other agents are plugging their type. So you can define the value from the surrogate to be the expected value that the agent gets from the produced outcome through the procedure I just mentioned. So now, as I mentioned, if you have the IC constraint for this surrogate allocation through the payments that you design and through the allocation that you pick, and also you have this distribution preservation property, meaning that after resampling the original type of the agent, the resampled type has the same marginal distribution as the original agent's type distribution, because also social welfare is an additive objective that decomposes across the agents, the entire black box reduction will be decomposed across the agents. So now your only goal can be designing a surrogate mechanism that satisfies the three properties on this slide: the single agent incentive compatibility, distribution preservation, and single agent welfare preservation. Okay, so let's go back to the surrogate mechanism problem and try to actually achieve this goal. Forget about the distribution preservation for a second. Let's say I have these possible surrogates. From each one of them, I can get a value that is equal to this expectation you see on this slide. And you would like to design a mechanism that has a good welfare and is truthful. So what would you do? The simplest thing that comes to mind is the following. So Rod, why do you do something weird? Why don't you just like calculate the maximum value here, give that surrogate for free to the agent? And definitely by definition, this is going to be an incentive compatible mechanism. There is no payment, payment is zero. At the same time, it achieves the maximum welfare among all the possible surrogates that you could assign to this agent. So in terms of welfare, this seems to be the best thing you can do. What can go wrong here? So here's what can go wrong. So think of these values. There are expectations over the type space of, over the randomness in the types of the other agents. So basically it's a summation over the type, the product of the type spaces of all other agents. So there are exponentially many terms in this summation, and even calculating this expectation is computationally hard. So you should not be able to even identify which one of these surrogates is the maximum one. But someone might say, hey, why are you doing something here? Why don't you just like sample from these values and then use the empirical mean? And remember, so each sample is going to cost you one call to the allocation black box, but still with polynomially many samples, you should be able to get a good estimate of these values and assign the one with the maximum, or the surrogate with the maximum to the agents. So here is what it can go wrong. Sampling errors can cause strategic deviations. And let's actually understand this through this very simple example. Let's say I have two surrogates. The agent can have two possible types, type 1 and type 2. Under type 2, agent always prefers surrogate 1 over surrogate 2. Under type 1, there is a randomness in the value. So in expectation, it prefers surrogate 1 over surrogate 2. But if you design a surrogate mechanism by sampling, then there is always a small possibility that you don't detect surrogate 1 is more preferable than surrogate 2, maybe an epsilon probability. And therefore, if the agent has true type 1, has always incentive to deviate to the type 2. And this might not actually give a lot of utility to the agent, but if you are shooting for exact Bayesian incentive compatibility, then with sampling, you cannot do anything here. So I hope this slide is kind of convincing everyone that there is a fundamental issue with sampling and you have to actually think about something else. So this something else is actually the magical toolbox that ended up to be the key to achieve exact Bayesian incentive compatibility in all of this line of research. And let me actually tell you what the Bernoulli factor is, and then I try to wrap up my talk a little bit quicker than normal. So a Bernoulli factor is a cute object. So suppose I give you a function that maps numbers from 0, 1 to 0, 1. And suppose there is a coin. The coin has unknown bias. Let's call that P. You don't know that bias. And I ask you the following question. Can you flip this coin, maybe as many times as you want, so that you generate a new coin with a bias equal to f of P without knowing P? Again, you might say, hey, Rod, this is a simple question. I flip your coin some number of times to estimate P, and then I just like flip a coin with bias is equal to f of P or f of P hat where p hat is the estimation you get. This cannot give you an answer to this problem because you actually need a new coin whose bias is exactly equal to f of v. And now you can see the connection between achieving exact Bayesian incentive compatibility and this problem. So I'm not going to go through the details. We'll be happy to talk about the details offline. So what we end up with is designing some Bernoulli factor based matching algorithms that assign a surrogate to the agent to do the type resampling. And once we come up with this resample type, we plug them into allocation black box, and the rest of the mechanism is going to be as I promised. So for the details, check the paper, just a little bit of advertisement that there are some interesting, simple combinatorial Bernoulli factories in this paper. We have a follow-up paper with Renato Paez-Lema and John Schneider that we basically answer the combinatorial Bernoulli factory problem as its most general form. Would be happy to talk about this extension as well.